So before we start the actual notes, let's just take a moment and answer these questions so I can remind you about limits. So the first one says, what is the limit as we approach 1? Now, there is no marker whether we're coming in from the left or right. So let's assume that we are having to match up from both sides. So if we look at the point right there at an x value of 1, from both the left and the right, we are heading to a height of 3. So our answer would be 3. For part B and C and D, those ones all go together. So let's look at B, C, and D. We are approaching 3. Now, as we come in from the left, that's what B notation is saying. We are at a height of 2. Oh, and actually E is going to go with it too. If we come in from the right, we are heading to a height of -2. So that means that the limit doesn't exist at 3, but f of 3 is colored in at the point or height of 1. So do you see how all of that ended up working out? Okay, does that make sense? Okay. Now, F, we are going to be talking about approaching -2, and all of these things are related to -2. So let's do each one of these individually. So the first one says coming in from the left, it appears that we are at a height of -1. Coming in from the right, it appears that we are at a height of -1. So the limit as we approach -2 is at -1. We don't care that the hole is there until we come to I. Now, I says, what is the actual function value when x is equal to -2? And what's the actual value it hits? -3. So that's just a little quick review of some of the things you need to know about limits, because section 1.8 that we're going to be doing is about continuity. And continuity is defined using limit notation. So we need to know what things about limits before we can actually answer something about continuity. Everybody good with that? Any questions? Okay. So we're going to talk about what it means for a function to be continuous. We're going to talk about the different types of discontinuities. Last year we talked about those. They were jump, infinite, and removable. So there are 3 discontinuities we're going to focus on, and how you can tell algebraically and how you can tell from the graph those discontinuities. So some of this will feel familiar. Last year I tried to use some of that language as we went through the process. We're going to talk about some of the theorems related to continuity, and then we're going to also talk about how symmetry can help us deal with some of these types of issues. Okay. So first, we have to look at our definition for continuous. A continuous function happens at A only if the limit, so we're coming in for both sides, is equal to the function's value that's filled in. So you're really saying that the limit equals the function value. So if the limit, so the left and right locations coming in equal the function value, then it is a continuous value in the function. So it requires 3 things. First, f of a has to be defined. It has to work. Then the limit has to exist, and then they have to match. So the first thing you always check is, does f of a work? The second thing you check, does the limit exist? And then the third thing you check is, do they match? We say if it is not continuous, we're going to use the word discontinuous or a discontinuity at that spot. So these are things we kind of know, but we're putting it into more formal language, into more of a calculus thing. So the stuff we talked about last year, we're going to apply a little more formally in this section. So the limit has to equal the function value. It's as simple as that. Last year, I talked about the fact that it would be a smooth portion of the curve that we couldn't lift our pencil. Because if we lift our pencil, that means that either the limit got disconnected, or there was a hole we had to jump across, or there might have been an asymptote we have to jump across. And so those are the kinds of places in the graph where we would consider a discontinuity. A graph might be continuous for all real numbers but one. It might be perfectly fine everywhere but one. So it's sometimes where you might just have one point in the entire function that is messed up. And that's pretty common. Everybody got what you see here? Okay. So let's look at this particular function. So let's assume, because they didn't tell us otherwise, let's assume that these two, it keeps expanding from left to right. Okay. Now, if we think about drawing it, let's think about where we have to lift our pencil. So if I was drawing this, I would have to stop here, jump, lift my pencil. Stop here, jump, lift my pencil. Stop here, jump, lift my pencil. Stop here, and I never have to stop again. Okay. So you really want to think about from left to right. Remember, so continuity, we're going to go from left to right. We're going to use interval notation. So this function is continuous on the following intervals. So we're going to go from left to right, like domain in a sense. The first value we had to lift our pencil was 1. The next value was 3. The last value we skipped was 5. So it is continuous from negative infinity to 1, from 1 to 3, from 3 to 5, and then from 5 to infinity. Now let's think about when we lifted our pencil. It is discontinuous at the points x equals 1, x equals 3, and x equals 5. We should see that we have skipped 1, 3, and 5. So the discontinuity is at an individual point. It is continuous everywhere else. Does that make sense? Does that make sense how the graph? This type of discontinuity is removable. This type is a jump. And even though we do have a spot up there, this one is a removable one. You kind of think I could remove the issue if I just put it down where it belongs. Okay, so that's example 1. Everybody good there? So the dot doesn't really matter. If you just have a little hole like these two, those are removable, and we'll talk about them more in a minute. This is considered a jump, and I always think I have to pick up my pencil and jump to the next spot, and that's a good way to remember them. Okay, so let's take a look at the algebra of this. So for the algebra of it, a fractional function, a rational function like a, will have a discontinuity where the denominator equals 0. Remember, the denominator isn't allowed to equal 0. There is going to be either a hole or an asymptote in the graph at that spot. Now, how do you know whether it's a hole or an asymptote? Well, a hole occurs algebraically. You will see 0 over 0 happen. A vertical asymptote occurs, you'll just see any other number over 0. So that's an algebraic test you can do. For A, the hole occurs when x minus 2 equals 0 or at x equals 2. So A is a continuous function except at x equals 2. If you plug 2 into this function, you get 0 over 0, which tells me it should have a hole in the graph. If we were to graph it into Desmos, this is what the graph looks like. It is a removable spot at x equals 2. You can see this little hole right there. So the math we got was 0 over 0 at that spot. Desmos will not, you might have to make a little sketch of the graph. Desmos will not necessarily visibly show an open circle there. But if you were to scroll your finger or do a little application that you can move a point across it, it will say 2 undefined. It will say 2 comma undefined. So it does tell you that, but you have to put your finger across the graph. It doesn't know it. It kind of simplifies it first, like we'll eventually do. And then it says, oh, that spot should have a hole. It doesn't just visibly show it. Maybe one day they'll actually add that in, but right now they don't, okay? So that is an example of a hole in the graph. Now, let's move on to B. Let's take a look at B. B is an example of a vertical asymptote. My earbud popped out. In the video, you're going to hear a poop. It makes a funky noise when it does. There's a vertical asymptote. And the reason is because if we do the math, it is undefined at 0. So hence, they did kind of warn us that. If you do the math, that's 1 over 0, which is a sign that we found a vertical asymptote. They filled in the point, but it didn't do anything. You can't fix the fact there's a vertical asymptote there. You can find a point that's defined at that location, but it doesn't fix the fact we hit a vertical asymptote. So if you look at the graph down here, that is a type of infinite discontinuity when we have a vertical asymptote. And so mathematically at that spot, you'll get a number over 0. And so then you're either heading to positive infinity or negative infinity. In this case, both are heading up because they're both, because there was a squared on there. If the power is even, they usually head in the same direction. If they're odd, they usually go in opposite directions, kind of like a rational function does. Okay. If you take a look at C, there is a problem again. Look at the difference between A and C. The only thing about A and C is it's still a removable discontinuity. We still have a hole because they didn't fill it into the right spot. You see how they put it in the wrong spot? For it to be correct, what they should have done is they should have filled it into the spot 2. Let me think what it would have been. It would have been 2, 4, 2, 2. I don't know, but they should have filled up the spot there and they didn't. So you can still have a removable discontinuity if they didn't fill in the right spot. If they wrote it like this and then they filled in the exact spot, we wouldn't have an issue, but they have an issue. And then finally, we have the step function here. We didn't do much with that. This is what it looks like. Sometimes piecewise functions will have what's called a jump discontinuity. And I think I have to jump up to the next step, the next piece. Anytime there's a break in the pieces and you have to jump from piece to piece. And it has a break at all of the integers. So there is an infinite number of discontinuities in this. At every integer, there is a jump. That is common in piecewise functions. Sometimes not. Sometimes the pieces match up perfectly. And then that might be you to find that edge piece what's happening on that border. Do the borders line up? Is one filled in, and does it fill it in the right spot? Those are all those things we will look at. But I just wanted to show you just kind of some common things that happen with a function. So vertical asymptote, look for a number over zero mathematically, a whole 0 over 0. A piecewise function, are the borders lining up? Those are the most common things. So we'll explore those, more as we go through the process. Okay, some things to know that are really nice. And I don't think, is there anything at all to write? Let's just highlight some stuff, okay? From the limit laws, if f and g are continuous and a and c are constants, then you can add the functions. They'll still be continuous at that same point. You can subtract them. You can multiply by a constant. You can multiply them. You can divide them. The only thing is you can't divide by 0. What makes it nice then, since polynomials are always going to work and they're continuous everywhere, then any combination of polynomials will work. Okay, so that's just what that last one's saying. A polynomial is continuous everywhere. A rational function only has problems where the denominator equals 0. Now you can find out if that is creating a whole or if that's creating an asymptote by doing the little algebraic trick, plug it in. If you get 0 over 0, you found a whole. If you get a number over 0, you found an asymptote. Okay, so the main thing to remember is polynomials are great. Since rational functions are made up of polynomials, they're going to be great except for where the denominator equals 0. That can cause you issues. So we'll practice all of these things. But the limit laws actually make us able to combine things and bring things together very nicely. So it still works for all the things we've thought about. So that's just what they're saying. Compositions, all these functions up here, as long as it's in their domains, they're going to work. So then it becomes, what are their domains? Polynomials, all real numbers, anything's going to work. Rational functions, don't let that denominator equal 0. Square roots, we can't have negatives in our square roots, right? Trig functions, sine and cosine work everywhere, but tangents and cotangents don't. Secants and cosecants don't. There's little asymptotes there. Inverse trig functions, we're going to talk about those more. We didn't talk about them too much last year. They do limit the domains there so that you don't end up with a repeat. Exponential and logarithmic functions, I'll go over those rules. Exponential ones, you might recall, look like this. So you can plug anything in you want to those. But these ones, you can only plug in positives because they're only over here. You can't plug a negative into a logarithmic ones. So their domains become important. And so I'll remind you of those domains as we go through the process, okay? Okay, so let's just look at one. Let's practice and let's see what I mean by all of this. I always try direct substitution. So the first thing we do is try subbing it in. So we're just going to plug it in and we're going to see what the mathematics tells us. If I plug in -2, I get -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times -2. Now that gives me -8 plus 8 minus 1 over 5 plus 6. I am going to get -1 over 11. Did I do anything wrong? Is that correct? Is that what you guys got? Okay. So what that tells me, from what we know, a rational function is just a polynomial on top, polynomial on the bottom. The only thing that screws this one up is the fraction 5/3. The only thing that's not in the domain is where that denominator equals 0, which is 5/3. So because of that, we're not approaching 5/3. we're approaching any other number, the limit is just -1/11. I am going to approach that. I'm going to hit it. I'm going to go through it. I'm not going to have any issues there. Now, if they told me what is the limit as we approach 5/3, then we have an issue. But because they asked us what's happening at -2, well, I don't know. I can just plug in -2. You see what you have to check for. You always try substitution in no matter what when you first look at it, because that's going to give you so much information, and it might just give you the answer. Okay. Let's look at this one. It says, where are the following functions continuous? Well, it says that the composition of two continuous functions will continue to be continuous. Anyway, this is the function. We'll call that f of x. One of the things you had to do on the quiz was you had to like pull apart. Oh, actually, let's call this g of x. You had to pull apart two functions and see what composed them. And then our outer function is, I don't know what changed to that. Our outer function, let's call that f of x, is the sine of x. So our inner function is x squared, our outer function is sine of x. Individually, each one of those are continuous everywhere. X squared works everywhere. I can plug in anything I want. Sine of x works everywhere. It's a constant wave. I can plug in anything I want. So if I combine them, I'm still going to get a continuous function. It's always going to be something. So this is continuous everywhere. Nothing messes it up. Okay. Now, let's look at B. Our inside function is 1 plus the cosine. Now, the cosine is a continuous function. Nothing messes it up. It is good to go everywhere. But our outer function, we'll call it little f, is the natural log. I can only plug in numbers that are bigger than 0. They have to be positives. So in this particular case, I know that the thing I'm plugging in, 1 plus the cosine of x, has to be greater than or equal to 0. So let's think about that for just a moment. Okay. So let's draw a little picture for a minute. The cosine function and please don't think this picture is going to be pretty, but it's going to be okay. Normally, our cosine function starts at 1, goes down to 0. There's a bump here and a bottom bump here. So it looks something like that. Would you guys agree? That's a cosine function. Now that wave, of course, continues to the left, to the right. I mean, it does its thing, you know. We know that. It keeps going on and on and on. If we pick it up and we lift it, and I apologize, it can't be equal to 0. But it has to be greater than 0, I'm sorry. Let's pick this function up 1, because hopefully we remember our rules of transformation, and this plus 1 just takes the graph of the cosine and goes, boop, lifts it up 1. So let's do that, okay? So now these points go up 1. So lift every point up 1. Is that graph always higher than 0, bigger than 0? No. Almost. Is that graph hitting 0 in a few places? That's the places that aren't going to work. That's the only places that won't work. So this function doesn't work. Well, let's kind of categorize those things. Positive pi and negative pi. The next ones that this will happen will not be 2 pi and negative 2 pi, but 3 pi and negative 3 pi, and then 5 pi and negative 5 pi, and 7 pi and negative 7 pi. If we looked at all of them, it'd be the odd multiples of pi. Now, let's think about notation-wise the mathematical way to write that. So it is continuous. Well, let's say it's discontinuous if x is an odd, so odd is 2n plus 1, multiple of pi. So we write odd as 2n plus 1. We write even as 2n. And what does the n stand for? The n can be any integer you want. So that's just n is an element of the integers. So that is the very mathematical formal way to say that. Now, if you said the odd pies and gave me a little list of some of them, I'm going to give it to you. But we need, because you're sitting in a calculus class and you might take future maths, then it's a good idea to start seeing that more formal notation. Pre-calc, I started introducing some notation. In this class, I'm going to try to use it more and more as we go, so that just to get you used to that notation. So this is just your integers, that z. I'll make it a capital Z with a little line through it because otherwise it kind of looks like a 2. This means an element of, or in that set, a member of the set, an element of, and n is just the variable I used for that particular number. That's very common. So this just means the odd pies. That's all it means, okay? So that one works okay, except for the odd pies, messes it up. You have to have a knowledge of the fact that a natural log, I can only plug in positives, and sometimes this hits 0. Now, if it was a cosine plus 2, it would be high enough that everything would work. But that cosine plus 1 makes it skim that that x-axis, and then it messes it up in some spots, okay? Another thing you can do is if you throw this graph into Desmos, because we have some people that like Desmos, you'll see that there is, I believe, either a whole or a vertical asymptote at each of those pies, negative pi, 3 pi, negative 3 pi, and so on. So that is another way. Graphing and the algebra should always blend together. If they don't, then one of those things is wrong, okay? Everybody good? I tend to go to the algebra first, but if I'm unsure of my answer, then I'll throw it into Desmos and go, does it seem to line up with my answer? So it just can verify that you're thinking right. My brain does tend to lend itself toward the algebra. It always has on it. Okay. So there are some functions that, is there anything to write on this one? No, okay. So there are some functions that only could be continuous from the left or the right of a particular number. So that just means that we land where we think we are landing as we're coming in from the right. We are landing where we think we're landing as we coming in from the left. So we can say it's maybe continuous on an interval. Every number in that interval works just fine. Examples of that. Let's say we draw a square root. And it starts at A. See how we can come in from the right and we'll land at that spot? But there's nothing over on the left. So this is a function that is continuous from the right of A, but it's not continuous from the left. If our square root was flipped the other way, that would be an example that it is continuous from the right or from the left, because the function continues on from the left without us having to lift our paper. So a one-sided continuity most likely happens in a square root. That's the one that we most categorize as just having kind of that one swoop to the left or to the right. So that's kind of just what they're getting at in that particular definition, is that there are some functions we can't evaluate a spot in both directions. I'm so sorry. So if it says to show that the function is continuous on the interval from 1 to 2, here's where this is something we can graph pretty easily. We know that the starting place of this function is where our inside x minus 1 is equal to 0, or x equals 1. So you should also recognize it's just taking the square root function and scooching it over to the right. And so our starting point would be at 1, 1. And then if you plug in 2, or I mean 1, 0. If you plug in 2, you get 1, and then so on. So our graph looks like that. So is it continuous on 1, 2? Well, sure it is. We can plug in 1 and get a valid response of 0. And then everything to the right of that is continuous. The graph shows us the continuity. So, sometimes you do have to rely on a graph, especially if it's an easy one. But if you think about the domain of this is where x minus 1 is greater than or equal to 0, or x is greater than or equal to 1. So that's one of those examples where 1 to 2 is in the domain. And that's another way. If you show what the domain is, we learn that root or rational functions and polynomials, all of those things, if it's a member of the domain, 1 to 2 is in the domain. So that is another way to verify that you technically are. So you can either talk about what the original domain is. Hey, this function works for anything that is greater than or equal to 1. So if I know that, then 1 to 2 is definitely a continuous spot. I never have to lift my pencil when I'm drawing that from 1 to 2. Okay? So that's kind of what they're getting at there. Now, here's kind of an interesting question. I've seen this in multiple places. It says, what is the constant c that will make this function continuous? Okay, now let's look for a moment. This portion of it is continuous because it's a polynomial. C is just a number, but it stops at 4. This is just a line. This one's a parabola. This one's a line. It's continuous, but it stops at 4. What is the only value that we have to worry about? 4. So what we're going to do is we're going to take x squared minus c squared, and we're going to plug in 4. We're going to take cx plus 20. We're going to plug in 4. We're going to see what happens when x is 4. So let's plug our x value of 4 into these functions, and let's see what we get. Well, in the first one, I get 16 minus c squared. And the second, I get 4c plus 20. What do we know? We need these two things to line up. We need those two things to equal the same value. So we just need, how can we get them to be equal so their heights are equal? How can we get them to be equal so they line up? So set them equal and then just do what you know about solving equations. I'm going to take the c squared to the right so that it becomes a positive. That's my highest power. It's easier to solve that way. So I'm going to make the left side 0. I'm going to get c squared plus 4c. I'm going to subtract 16 from both sides, and I'm going to get plus 4. Now that's a quadratic. Hopefully you know the correct methods to solve a quadratic. The most common is to factor or use the quadratic formula. Whatever floats your boat. If you like the quadratic formula, go for it. If you're a factoring person, hopefully by now you recognize that this is c plus 2 and c plus 2. So there's just one value where c plus 2 equals 0. So c would have to be negative 2 for those two things to land in the same spot. Now you can check if x is 4 and c is negative 2 for the top one, you get 12. If you plug c as negative 2 and x is 4 for the bottom one, you get negative 12. So they would line up perfectly at that spot. So that's all that's saying. Okay, when x is 4, that borderline, what c value would make them match? So we got to make a match. And so all you do is you plug in the border value first, then plug in the border value first, And then you're going to set those two things equal to make their heights equal. And that occurs when c is equal to -2. Makes sense? Maybe a little bit. Okay. Now, let's see where we're at. Let's do these next two slides and then we'll stop. There's going to be two different types of intermediate value theorems. This is a continuities intermediate value theorem. And it says, suppose that we have this continuous function from a to b. And if we pick any height, some number n, so we've got this continuous function, see this continuous function? If we pick some number n, there will be some f of a and f of b that is between, that n is some number between f of a and f of b. And let me show you what they mean for the picture. Yeah. So, so if we look at f of a, it's right here. F of b is right here. There exists some c such that f of c is equal to n, and n is between f of a and f of b. So you see how there's, see here, there's a spot here and a spot here and a spot here. There's some function value in between. And it has to be, it's basically because of the fact that we never lifted our pencil. Somewhere we have to cross over that number that's between them. Now, you might think, who cares? What this helps us to do, and actually what computers do when computers were first trying to like solve polynomials and do mathematical equations, the intermediate value theorem helped them kind of whittle down until it found the zeros. So it was very powerful finding zeros that weren't like nice because you couldn't find them real great quickly. It allows us to kind of pinpoint those because we can keep getting closer and closer until we whittle it down. So that's kind of where the values in between two values. Okay, so let me show you where it's helpful. It says, show that there is a root of the equation between 1 and 2. So the root of an equation is, remember, where the function is equal to 0. So we're just saying, hey, there's a 0 somewhere between 1 and 2. Well, this is what's so nice about this. This is a continuous polynomial. And polynomials are great. So if we call our polynomial f of x, and then we're going to just write that negative 4x cubed minus negative 6x squared plus 3x minus 2. Let's plug in 1 and let's plug in 2. If you plug in 1, you get 4 minus 6 plus 3 minus 2, which is negative 1. If you plug in 2, you get 32 minus 24 plus 6 minus 2, which is 38 minus 26, is that 12? So because it's continuous, because I went from a height of -1 to a height of 12, don't I have to cross over 0? That's what the intermediate value theorem is useful for. The fact there has to be, I had to cross over 0 to get to the other side. So there is a root or a 0 between 1 and 2. That's all it's saying. I will have so many students that miss that question on a quiz or a test. It is as simple as, if it's continuous and one end is positive and one end is negative, you crossed over 0. That's as simple as it is. So don't make it harder. It's just applying the rules of continuity in a useful way. If it's continuous, I never lifted my pencil. I was at -1. I went up to 12. I had to cross over 0. Now, how could you pinpoint it further? Instead of 1 and 2, we could squish it in a little bit and make it 0.8 and 1.8. And then, is it still positive and negative? Did it switch again? And you could keep doing that. And that's kind of what computers had to do at one point. as far as whittling down what those zeros are. Okay, so we're going to stop there. We'll continue these and finish this up tomorrow. There you go. We're going to continue 1.8. It's still not working. There we go. And I'm going to remind you some things about symmetry. We already touched upon this last year a little bit earlier, but remember that an even function, if you plug in negative x, that is going to go away, because if positive f of x is on there, at negative x, you're going to be at the same height. And that's just because you have that ability to fold it across the y-axis, so it has y-axis symmetry. An odd function, remember, you can put a push pin at the origin. It has origin symmetry. Now, when is this going to be helpful? Well, there's going to be some times later on in this course where we will need to do some pretty interesting calculations. And if we can use this symmetry, we actually can do things a little bit quicker, because we can maybe start at 0, get an answer, and then just double it, because we know like the symmetry of this one. Or this positive piece on our odd function might cancel out the negative piece, and so your answer is 0. So by knowing the symmetry of a graph, or just by looking at the function, we can tell some easy things about that function. So that's all that's reminding you of, and that's why we focused on it a little bit earlier as well. So this should be review, but let's just go over. Remember, if it is even, f of negative x and f of x match. If it is odd, here's one I noticed that on the quiz you guys were messing that up a little bit. It's like I just multiplied the entire function by -1. So you have to picture what does that look like if I would multiply that function by -1. So what we're going to do is we're just going to do that algebraic test. We're going to plug in negative x. We're going to see, is it like I multiplied through by -1? Is it back to its original form? If some of the pieces were multiplied by -1 and some of the pieces were not, it's neither. So if we look at this first one, if I plug in negative x, what happens is we could picture that we multiplied -1 by the entire function, right? That's just the opposite of our original function. So since this is the opposite of the original, we know that it must be odd. If you were to pull up Desmos and look at a graph, this graph goes through the origin. So odd graphs either go through the origin, they could have an asymptote there, but they go through the origin, or they have a symmetry about the origin. So if you do a little, I call it a flip. If you flip over the x and then immediately flip over the y, you'll get a piece that matches. So if you have a piece in 1 and 3, or if you have a piece in 1, you'll have a piece in 3. If you have a piece in 2, quad 2, you're going to have a piece in quad 4 for an odd function. So g of x goes right back to the way it starts. So it matches the original. So it's even. So if we were to put that into Desmos, it kind of looks like a parabola. It's pointing down and lifted up 1. It's perfectly symmetric about the y-axis. Okay. And then for h of x, if we plug in -1, or negative x, I'm sorry, one of the pieces changed, but one of the pieces did not. So half of it changed and got multiplied by -1, but half of it did not. So it's neither. If you go and draw that, that is a parabola. It's pointing upside down. don't expect this to be a perfect picture. But it looks something like this. Does it have origin symmetry? No. If you did a flip with it, it would just make a parabola on the other side. You can't fold it across the y-axis anymore because its vertex is up there. So it's a neither. So the power of that is going to come later on. Knowing that symmetry will make some of the calculations we do go a little easier. That's why we focus on it now, so that you remember those rules. So when we get to the rules that it's going to be more complicated, we'll be able to, go from there, okay? So then that leads us to your assignment. So you have the rest of class to please work on section 1.8. Those are just the odds there. You do have your solutions, so I want you to be checking them as you go. I made it due Monday so that you could, if in class Monday you had questions or were stuck on any, you could ask. But I need intelligent questions, not just do every one for me. I got stuck on problem number 17. Give me the ones you're really stuck on and I will help you. So that's it. There you go.